Hi, I'm François Tallet. I'm a product marketing engineer in VCF Networking. We're going to talk about modernizing network infrastructure with NSX in VCF. The public cloud is built on software-defined networking or SDN. VMware NSX is an inherent part of the cloud foundation and allows IT teams to deliver similar cloud-like capabilities into the data center. VMware NSX abstracts the physical network layers by using software to manage things like routing, switching, and firewalls, which makes private cloud networks more flexible, scalable, and easier to automate. NSX works with Kubernetes and gives container reliable and secure network connections, just like virtual machines. NSX helps monitor network traffic in real time, making it easier to find problems and improve performance. NSX allows applications to move between different cloud environments without changing their network or security settings. And finally, the VMware vDefend add-on provides strong security tools to protect your data and application using smart technologies and software-based network systems. The new era of networking isn't about hardware configuration anymore. It's centered around the application. VCF delivers SDN through NSX and its add-ons. It allows you to visualize your application networks and security topology, apply automated security policy recommendations, and monitor traffic continuously. The core idea of software-defined networking is to build a standardized, repeatable infrastructure by abstracting away the complexity of physical networking. And because SDN is policy-driven, compliance is easier to maintain and enforce, tailored to each application's requirements. From an operational standpoint, enforcement is centralized and applied at the VM level instead of relying on multiple touch points across the infrastructure. Sure, the hardware configuration becomes simpler and more consistent, focused primarily on providing redundancy with high availability. The physical layer remains, but it simply serves as a transport foundation for the software-defined network. So, how NSX network is different from the original vSphere networking? When VCF uses vSphere networking, coordination with a physical network is absolutely essential and necessary. For example, deploying a new application involves attaching its VMs or containers to DV port groups. Those DV port groups must be then mapped to corresponding VLANs in the physical infrastructure. Even with advanced technologies like EVPN in your physical infrastructure, coordination between application and network teams remains necessary. Beyond layer 2, deployments may require changes to routing, load balancing, security, and more often involve multiple teams. And in many organizations, this interaction rely on ticketing systems, introducing delays that can span weeks. Furthermore, the number of independent configuration touch points makes end-to-end automation extremely difficult, if not impossible. So VCF includes NSX virtual networking. With NSX, workloads can be connected to virtual networks that are completely independent of the physical infrastructure. For example, here we create a virtual network X using NSX. The VMs attached to this network immediately get L2 connectivity. No additional configuration is needed anywhere else. How is this achieved? Well, NSX automatically establishes tunnels between the hosts. No user intervention is required. And when traffic for virtual networks need to be carried between hosts, NSX encapsulates it and sends it over the physical infrastructure. The physical network only sees IP traffic between hosts. It's unaware of the underlying virtual segment which exists entirely within NSX. This allows NSX to instantiate any number of virtual network over the same set of tunnels without requiring any configuration on the physical network side. Of course, NSX offers much more than just virtual layer 2 networking. In fact, NSX builds a complete virtual networking stack on the top of those virtual networks. With NSX, the intelligent services that were provided by the physical appliances are virtualized. There's no need to manage complex and costly services appliance in the physical network. With NSX, all you need is simple IP connectivity between your components. Application deployment now only involves configuring virtual components. And because all those components are managed by NSX, you can deploy your application through a single configuration point. Thanks to NSX intent-based model, multiple networking features can be even configured in a single REST API call. This architecture also makes automation straightforward. These benefits are well established in the public cloud, and with VCF, which integrates compute storage and virtual networking, you now get the same experience in your private cloud. NSX Virtual Networking unlocks several additional use cases. In traditional data centers using physical appliances, workloads are often tied to specific locations, creating silos and limiting flexibility. With virtualized networking, workloads become mobile. VMs can move freely across a data center, enabling optimal compute utilization and better redundancy. Because NSX virtual networks operate over basic IP connectivity, they can be extended across racks or even between data centers without requiring complex overlay deployed throughout the physical infrastructure. Virtual networks also form the foundation for simplified disaster recovery. When a site fails, its networking environment can be instantly recreated at the backup site, supporting redeploy or even pre-existing workloads. And finally, multi-site deployments are also possible. NSX allows dynamic extension and instantiation of networking infrastructure, all managed from a central control point. NSX is automatically deployed through VCF operations. At the core of NSX is the NSX Manager, which handles both the control plane and the management plane. In smaller environments, this NSX Manager can run as a single virtual machine protected by vSphere HA. More commonly, it runs as a cluster of 3 VMs for scale and redundancy. The NSX Manager is tightly coupled with vCenter, which acts as the compute manager for the system. Both components connect to a shared VM management network within VCF. Each ESX host is automatically configured by VCF with tunnel endpoints or TEPs. These TEPs enable virtual network traffic that run over the NSX overlay network. NSX can also use edge nodes virtual machines to provide network services that require centralized processing. Those are optionally deployed from vCenter. On the top of the VM management network, these edge VM have their own TEPs connected to their own NSX overlay network or edge overlay network. Whether it's NSX overlay or edge overlay network doesn't really matter. What matters is that the TEPs, whether on host or edge nodes, have IP connectivity with each other. That's all. A key service that runs on NSX Edge Node VMs is the Tier 0 gateway. This is a virtual router that connects the NSX environment to the physical network. It peers with external routers with BGP and allows NSX to dynamically advertise newly created networks and receive traffic destined to them. The deployment of the Edge VMs, as well as the creation and basic BGP configuration of the Tier 0 gateway, can all be done directly from vCenter with a simple guided workflow. Here is a selection of the key features offered by the NSX Virtual Networking Stack. Stateful services typically run on edge nodes, which act as centralized service appliances. And while NSX includes core networking capabilities out of the box, advanced security features are available as add-ons. A virtual private cloud, or VPC, is a logically isolated tenant-specific virtual network that provides dedicated routing, switching, and security services. In VCF9, VPCs are implemented consistently across the entire platform, not just within NSX. This model defines clear roles to support multi-tenancy and enable self-services capabilities for end users. The first role is the enterprise admin, who owns the VCF physical infrastructure and manages the connection to the physical network. The enterprise admin is responsible for coordinating with the physical network to ensure proper connectivity. They also create projects which represent the first level of tenancy and define external IP blocks that allow communication between the virtual and physical networks. These external IP blocks are then distributed to the individual project, and quotas can also be applied as needed. Importantly, the enterprise admin maintains full control over all networking resources. Next, the project admin steps in to manage the resources delegated by the enterprise admin, but without direct access to the physical infrastructure. The project admin is responsible for creating and managing VPCs, which represent the second level of tenancy. They also allocate resources such as IP pool and apply quotas to the individual VPCs. Finally, we have the VPC admin, who acts as the end user in this model. The VPC admin can independently create virtual networks called subnets and easily attach workloads to those networks. A key benefit of this model is that the VPC admin can fully leverage networking services without requiring in-depth networking expertise. This is possible because the enterprise and project admins pre-configured the underlying network and resources allocation, enabling true self-services with minimal need for additional support. The VPC concept has long existed within NSX, but with VCF9, it is now fully integrated and consumable across other components of the platform. VCF automation leverage VPC object, and the VPC are now exposed as first-class object directly within vCenter. By default, NSX creates a default project that is fully configurable by vCenter admin, who in that case serves as the enterprise admin, project admin, and VPC admin all at once. Other non-default projects appear in vCenter as read-only and cannot be modified from there. You need to have access to NSX and the appropriate role to do so. vCenter also displays subnets directly into the UI, allowing you to easily connect a VM to a subnet, similar to how you would attach a VM to a DVPG. In fact, both options are available side by side in the interface. NSX edges are essential service appliances within NSX architecture. Their deployment requires careful alignment between DV port group and VDS uplinks on the ADSXi hosts and NSX Edge fastpath interfaces, and often complex tasks for less experienced users. A new deployment workflow now integrated into vCenter UI simplifies this process by guiding users through the necessary inputs, automatically mapping vSphere and NSX object, and providing real-time visual representation of the configuration. This significantly streamlines the deployment of HVMs, a critical component of NSX. We've seen that the VPC model defined three distinct roles, each with clear responsibility. Now, let's look at how those roles work together to establish connectivity and the key object involved in making that happen. The enterprise admin manages interaction with the physical network and provides connectivity options to project admin by defining external connections. These external connections are profiles that describe how access to the physical network is delivered. An external connection can be represented either as a connection centralized through a tier 0 gateway, or an edge node, or distributed directly via a VLAN. The project admin, who has no direct access to the physical infrastructure, manages a new type of gateway called the transit gateway. By attaching the transit gateway to an external connection exposed by the enterprise admin, the project admin defines how the project connects to the external network. The choice of external connection also determines whether the transit gateway will function in a distributed or centralized mode that we'll see later. Finally, within each VPC, a VPC gateway is deployed. The VPC gateway connects internal subnets and provides external connectivity by routing through the transit gateway. It is not directly seen in the UI. When attached to a centralized external connection, the transit gateway is associated with a tier 0 gateway or on an edge node. It effectively acts as a VRF of the tier 0 for those familiar with NSX. This tight integration means that all north-south traffic through the transit gateway also flows through the tier 0 gateway and inherits its redundancy model, whether active-active or active standby. This has direct implication on the services the transit gateway can deliver. Stateful services are not supported when operation is in active-active mode. Similarly, VPC gateways also require a centralized component on an edge node to run stateful services. However, VPC gateway can be assigned edge node resources independently of those used by the transit gateway in a centralized external connection setup. Services such as SNAT, DNAT, DHCP, QoS, gateway firewall, supervisor cluster integration, and VCF automation with modern UI all require edge nodes. VCF 9 introduces the capability to deploy VPCs without requiring edge appliances. This simplifies significantly one of the most complex tasks in NSX. By attaching a transit gateway to a distributed external connection, each ESX host can independently route VM traffic to the external network. This model comes with trade-off, however. Only basic services like reflexive one-to-one NAT and distributed DHCP are available, and the physical network must provide a shared layer 2 domain across all ESXi hosts. Unlike traditional NSX overlay networking, this approach requires external VLANs to be extended to each host. Finally, let's talk about Enhanced Data Path or EDP. EDP is a high-performance virtual switch with two modes of operation, standard and dedicated. By default, new VCF deployments run EDP standard mode on the VDS, while upgrading VCF 9 will not change the VDS mode. Like the original VDS, the EDP VDS is interrupt-driven and uses CPU cores on demand. However, with DPDK-based operation and packet and a new packet data structure, it offers higher performance across all workloads without any tuning necessary. EDP delivers a 50 to 70% increase in performance, improving both bandwidth and packet per second for workload exchanging at a high rate of small packets. EDP drivers optimize NIC performances. Even for older PNIC with limited feature, we will see improvement compared to the original VDS operation mode. Finally, the dedicated mode assigns specific CPU cores for packet processing, offering even better performance for standardized workload. It requires tuning based on careful consideration of traffic type and average packet size, and is typically used in telco environments. The legacy standard non-EDP VDS mode remains available if needed anyway. That's all for the networking part. Thank you.